Hello and welcome to my physics video lecture supplement series. In today's video I wanted to do something a little different than what I've been doing with these supplements so far, which is that instead of working through just one simple example, 5, 10, 15-minute example, I want to go over some concept that's been giving a lot of people a lot of trouble. It's a concept that gets used in both the physics classes and to some extent the physical science class. And that concept is basically what happens when you have a parabola and you square one of the axes of the parabola. Why would you do that? What does it do? Etc. And so what I want to do is sort of show this via an example of sorts, and basically work it as follows. Imagine that you have just done some experiment. It could be, I don't know, a position versus time experiment in which you have some object moves across a table, and every couple seconds you mark how far it's traveled, for example. So you write out your data, and it looks something like this. Time in seconds, and you take readings every 2 seconds. So let's say you get one at 2, 4, 6, 8. Maybe something goes wrong. You don't get the one at 10, but you get one at 12. And let's say that when you take these measurements, you end up also taking a set of distance measurements, distance traveled. And let's say that the distances traveled you mark as 2, 8, 18, 32, and 72. Okay? So presumably you have this as your independent variable, which I'm going to label x. This one is sort of your dependent variable y. And you decide to take this data and make a graph of it. So we have a distance, and then we have a time. So you pull out your graph paper, you make your delineation. Let's say that this is my graph paper. Maybe every little black tick mark on here is 10, or let's say 10 meters. Let's call it, I don't know, 10 seconds in this direction. Okay. So the points are going to be 2, 2, 4, 8, 6, 18, 8, 32, 12, 72. So 2, 2 is probably down here somewhere. Next one was 4, 8. So 4 is about here, 8 is about here. Next one was 6, 18. So 6 is going to be about right here. 18 maybe is getting up to around here. 8, 32. So it's right around here. And 12, 72. So 30, 40, 50, 60, 70. Gets us right around here. So if we were going to draw this, first of all, probably you would be doing this on one piece of graph paper. Maybe you'd use a little better choice of scale than what I've picked. There's a reason why I picked this scale that we'll get to in a moment. You should really fill out as much of the graph as you can. But in any case, this thing right here ends up looking like some curve. And the question ends up being, what kind of curve did we make with this data? Is this is it a parabola? Is it an exponential? Is it something else? So what is it? And the test that I'm going to use shows us whether or not this curve is a parabola. Now, if it is a parabola, you see that it's going to be a vertical parabola, and that means that it should look like y equals x squared, or y equals something times x squared. So that means that the axis that we're going to need to be squaring is the x-axis. So I'm going to create a new variable. I guess we'll call it capital T. And capital T is little t squared. In other words, what's going on to the capital x-axis is little x squared. So take these numbers and square them, and that's this. So this is 2 squared, which is 4, 4 squared, which is 16, 6 squared, which is 36, 8 squared, which is 64, 12 squared, which is 144. Okay, and we need to make our new graph. I'll go ahead and leave this old one up. Realistically, you'd be doing this by putting it on a new, fresh piece of graph paper. I don't have time to make up a new, fresh one. So I'm going to put whatever variable t is in seconds squared on this x-axis, and we'll leave distance on the y-axis. So we see that we need to have 4, 2. So 4 was here, 2 was here. That gives us a dot right around here. We need to have 16, 8. So that's probably around here. We need to have 36, 18. Be about here. And we need to have, excuse me, this one, I'm a little off here. This one actually was 8, so that actually puts it only about here. This one was 36, 18, so that puts it in line with this point on this one. So it's here. 64, 32. So 32 is about like this. Puts it in here somewhere. This whole dot is actually a little off. Miscounting fail. And then our last one should be 144, 72. So that's out here, that's up here. So eyeballing it, maybe about here. So if we pull out a nice straight edge, whoops. Mine is slightly warped on one side, unfortunately. And then our nice straight edge, you can see, let's make this point big enough that you can actually see it. It's big enough. Our nice straight edge actually more or less goes through all of the points. So all these guys make a nice straight line. That means that we can write y equals mx plus b, because that's true for any line. And actually, since we're really using the capital x-axis, it's y equals m capital X plus b, where this one is slope, and this one is intercept, specifically the y-intercept. And let's go ahead and draw ourselves a nice line through these points so that we can get a slope. Oops. It's a good big straight line. You can see all the points fall on that line of best fit. What we got to do then is this y actually represents a distance. So really we have d equals m. The big X is really a t. So we can write that. And we need to find a slope and we need to find an intercept. So the intercept, you just look and see where does this line actually intercept the y-axis. So the intercept was at 0 seconds squared, comma 0 meters. So the intercept is 0 meters. So B is 0 meters. We need 2 points on the line in order to get a slope. So here's one of the points, might as well use it. Another point maybe would be around right here. So this point right here looks like about 100 seconds squared, comma 50 meters. So to get the slope, we do rise over run. And so that's going to be 50 meters divided by, 50 meters minus 0 meters divided by 100 seconds squared minus the 0 seconds squared. So 50 over 100, that's going to be 0.5 meters per second squared. Okay, and then big T is in fact little t squared. So we can rewrite this equation in its final form now that we've solved for all of these slopes, intercepts, etc., to say that d is equal to 0.5 meters per second squared times little t squared. And so this does in fact have the same form as y equals some constant times x squared. Which is the same as a vertical parabola. So what we've found is that by squaring this x-axis, we changed our vertical parabola into a straight line from which we could get a slope, specifically this number here, and from which we can also get a nice complete equation. So there's other things that could happen. For example, maybe instead of getting a vertical line, we'd get a vertical parabola, we'd get sort of a horizontal parabola. When this happens, then we square the other axis. So we square the y-axis and leave the x-axis alone, and you'd end up with something that looks like y equals square root, whatever the slope is, times x. And you might have something that's exponential, in which case you take a logarithm of an appropriate axis, and so on. So that's it for today, and I hope you found this helpful. Thanks for watching, and so long.